Welcome back to Statistical Methods. This is Week 10, Lecture 1, where I will be continuing to cover ANOVA, or Analysis of Variance, which we began with last week. So just some recap. One-way ANOVA addresses the question of whether there is an effect of an independent variable on a dependent variable when there are more than two levels or more than two groups of the independent variable. So the null hypothesis is that there are no differences between group means on the dependent variable. And the research hypothesis is that there is some difference between the group means on the dependent variable. So the way we detect an effect of our independent variable on our dependent variable in the form of a difference between group means is by estimating the population variance in two different ways. So the first way is based on the variance between individuals within each group, or within group variance. And the second way is based on the variance between group means, or between group variance. So if the null is true, these two estimates will be based on the same thing: random chance variability in scores that is not due to our independent variable. In this case, the ratio of between subjects and within subjects variance should be around 1, which will lead us to fail to reject the null hypothesis. However, if the null is false, the between groups variance will reflect both random chance variability and differences in our underlying population means. Now, if this is the case, the ratio of between subjects to within subjects variance will be greater than 1. Now, if this ratio is sufficiently large and very improbable, assuming that the null hypothesis is true, we will reject the null hypothesis and conclude that our independent variable has some effect, that our population means are different. So today we'll learn how to calculate the between subjects and within subjects variance based on multiple groups to get this F ratio, allowing us to test a research hypothesis about differences between multiple group means. And by multiple, I mean more than 2. So let's start out with an example. An evolutionary psychologist wants to study people's ability to recall a list of words as a function of how that list of words is initially encoded. And the sample size is 15 participants, so they're recruited and randomly assigned to one of 3 experimental conditions. So 5 participants in each of those conditions. Now, all participants see the same list of 20 words and are then asked to rate these words on one of the following 3 dimensions. But this dimension depends on their group assignment. So one group rates it on self, so how relevant that word is to themselves personally. Another group rates it on how relevant the word would be to a survival context. For example, trying to survive in the woods for several days without any supplies. And the third group rates that word on pleasantness, so how pleasant is that word? 1 week later, participants are asked to recall as many of the 20 words from the list as they can. And the dependent variable, or what the researcher is measuring, is the number of words remembered. So this psychologist first just wants to test the hypothesis that memory for words will differ across the 3 groups. The results of this study are located in the spreadsheet Adaptive Memory on Blackboard. And note that we'll start calculating S squared, or the estimation of population variance, using the Excel function equals VAR parentheses. Thus, whenever S squared is required, you can now use this function instead of finding the SS, the sum of squares, and dividing by the degrees of freedom. And this should save you a good deal of time. So to test the hypothesis that these 3 samples are taken from populations whose means are not equal, we'll need to calculate the following: a population variance estimate based on the variation of the scores within each of the samples, the population variance estimate based on the differences between the group means, and the ratio of the 2, so that is the between groups estimate of population variance and the within groups estimate of population variance. And if you recall from last week, this is referred to in ANOVA as F, which is our primary test statistic for testing differences on a dependent variable between multiple independent variable levels or groups. So the numbers we calculated steps 1 through 2 were the estimates of population variance based on our within group and between group variances are referred to in ANOVA as mean squared within and mean squared between. Mean square here denotes, or MS here denotes mean squares, or the mean squared deviation score. But you have to note here that these are conceptually equivalent to S squared, the usual population variance we've learned to calculate, which you should remember is the average squared deviation score, the same thing as a mean square. So it's just simply a change in terminology. The population estimate of variance here in ANOVA is referred to as mean squared. And since we have two of them, we have mean squared within and mean squared between. But this is the same thing as S squared within and S squared between. So figuring the within group estimate of population variance involves getting the S squared for each of our groups, so sum of squares divided by df, but instead we're going to use this equals VAR function to save us some time. And then pooling these estimates to get mean squared within, the within group estimate of population variance. Here, because our three groups have the same number of participants, we can take a simple average of our three S squared estimates to get our mean squared. So let's move over to Excel to look at how we do this. So here we are in the adaptive memory spreadsheet in Excel. And let's start out by calculating the estimate of population variance, the within estimate of population variance. So let's start by calculating S squared for each of our three groups. So here we have our scores in each of these through memory encoding conditions. And here are the scores on how many words participants received a week later. And again, we're looking for some difference between these groups on the number of words they recalled. But to calculate this within group estimate of population variance, we need to start by calculating the estimate of population variance for each of these three groups. And again, remember we could use this equals VAR function. So that would be equals VAR A3 through A7. And there it is, as simple as that. No need to calculate sum of squares and divide by degrees of freedom. Now for the next column, equals VAR, open parentheses, B3 through B7. And finally, equals VAR, open parentheses, C3 through C7. So there are our three variances. Now, if you remember, we need to just simply pool these to calculate mean square within. And all we need to do there is average them together since the same number of participants exists in each group. So average F6 through F8. And there you have it. That's our mean squared within, or our estimate of population variance based on within group variation. So let's move back over to the PowerPoint to move on to how to calculate mean square between, the other component necessary to calculate an F ratio, keeping in mind that this variance is due to random chance. And if the null hypothesis is false, mean squared between should be due to random chance, but also some effect of our independent variable. And we're going to eventually take the ratio of these two variance estimates to get our F ratio, which will help determine whether the amount of variance due to our independent variable is enough to deem this effect significant. So let's move back over. So if you look down here, here's our calculation of mean squared within, and it checks out to what we just did in Excel. So just taking the average of those three population variance estimates based on within groups variation equals 10.77. Now, figuring the between group estimate of the population variance involves estimating based on our observed sample means the variation of the distribution of sample means, or S squared of m, and then working backwards from S squared of m to estimate the population variance, or S squared. Now to get S squared of m, we have to treat the sample means like we typically treat individual scores when getting S squared. So we calculate the grand mean, or the mean for all participants in the study, calculate each sample mean's deviation score from this grand mean, so each sample mean minus the grand mean, square these deviation scores, and then sum them to get a sum of these squared deviation scores. So we are calculating a sum of squares here. And then we divide this by the degrees of freedom between, which is equal to the number of groups, so in this case 3, minus 1. So our df between here should be 2. So let's go calculate S squared of m. Okay, so the first step is to calculate each sample mean, which should be as simple as averaging across these 3 columns, within these 3 columns. Average A3 through A7. And I think we could just pull that down. No. So in the second one, we would have to do average B3 through B7, and then average C3 through C7. Right, so we just found averages for these 3 columns. Now we need to calculate our grand mean. We have a place for that right here. So we could just average F2 through F4. So average F2 through F4. So averaging across our 3 means. So our grand mean is 10.3 repeating. Now we need to calculate these deviation scores. So this should be equals 12. Well, let's just do the sum. F2 minus our grand mean, which is in F10. But let's do the $sign function so we can do a pull down. Yep, so this is going to be F3 minus F10, and this is going to be F4 minus F10. Now we need to simply square these. So equals G2 squared, and we can pull that down to get G3 squared and G4 squared. So the next step is to sum these square deviations up, and we can do that right here. So equals sum H2 through H4. And remember, our degrees of freedom between is equivalent to the number of groups minus 1, so equals 3 groups minus 1, 2. And now we divide the sum of these square deviation scores by our degrees of freedom between to get S squared of m. So equals F11, divided by F12, and that is our S squared of m, 4.01. Let's go check out if that works out with what we have in the slide. And no surprise, it does. So S squared of m equals 4.01. So now we'll use this S squared of m, or the variance in sample means, to estimate the variance of the population of individual scores, or mean squared between. So previously we have used S squared of m equals S squared divided by n. So to get S squared between, or mean squared between, we will multiply our S squared of m by the number of subjects in each group. So little n, which for us is 5. So let's go back to Excel and do that. So to calculate the mean squared between, we need to multiply our S squared of m by the number of subjects in each group, which in this case is 5. So mean squared between equals S squared of m, which is in F13, multiplied by 5, the number of subjects in each group. And there is our mean squared between. So does it check out? Yes, it does. Mean squared between equals 20.07. So now we can finally calculate our F ratio, which is again the mean squared between divided by the mean squared within. So let's move over to Excel and do that. So F equals mean squared between, F15, divided by mean squared within, F16, and we get an F of 1.86. And this checks out. F equals 1.86. So now that we have calculated our F statistic, we'll need to know what cutoff value to compare it to, so that we can determine whether our result is statistically significant. In other words, whether our 3 group means differ to an extent that would be expected to occur only about 5% of the time, if the null hypothesis is true. So that's assuming a significance level, of course, of 0.05. So to do so, we'll need to use this F distribution, asking how likely is our F value to have come from a distribution of F values that assumes there is no variance between our 3 group means. Now, the shape of this F distribution, and thus what the cutoff value will be, relies on 2 types of degrees of freedom corresponding to the 2 estimates of variance that are used to calculate the F ratio. The between groups degrees of freedom, which we already calculated, the number of groups minus 1, and the within groups degrees of freedom, or the denominator df, which is the total number of participants minus the number of groups. So in this case, 15 participants minus 3 groups equals 12. Right, so here that is. Degrees of freedom between, number of groups minus 1, 3 minus 1 equals 2. Degrees of freedom within, total sample size minus the number of groups, 15 participants minus 3 groups equals 12 for the degrees of freedom within. Now to determine the cutoff ratio that tells us whether our result is extreme enough to reject the null hypothesis, we need to know the numerator degrees of freedom, the denominator degrees of freedom, and the desired significance level. And as per usual, we'll have 2 options for determining what cutoff this value is, using the F table or the Shiny app. So using the table is fairly straightforward. Look up your denominator degrees of freedom in the first column, then match it to the significance level options, 0.01, 0.05, and 0.10, and numerator degrees of freedom between 1 and 6. So here are your denominator degrees of freedom in the column, and in the row you have your numerator degrees of freedom. Column 2 is your significance level, which will be 0.05. So we had a 12 denominator, so we could read down through this column all the way to 12. And 2 numerator degrees of freedom, assuming we want to use a cutoff of 0.05. This should be our cutoff. An F of 3.89. And you can find the Shiny app at this link here. And this is the recommended way to do it. And it's the same as always. You enter your numerator degrees of freedom and your denominator degrees of freedom. And you enter your probability, so 0.05. And it gives you the cutoff value, which is 3.89. So remember that since the F ratio is based on variances or average squared values, it can only take on values greater than 0. So because negative F ratios don't exist, we don't need to worry about the tailedness, so one or two-tailed tests for F tests. All F tests are one-tailed, so they isolate 5% of the probability distribution in the right tail. So if our positive F passes that cutoff score, we can reject the null hypothesis that our means are equal. So in order to reject the null hypothesis, our sample's F ratio will need to be greater than 3.89. But what was our samples? 1.86. So the conclusion is that we have failed to reject the null hypothesis, concluding that our sample means are not significantly different from one another. Now notice that our survive group actually did remember about 3 to 4 additional words on average than our other two groups. Now, intuition suggests that this might be a practically meaningful difference, yet our result was not significant. Now, why is this? Primarily because our sample size was so small. Remember that smaller sample sizes means less precise, that means more variable, estimates of the population parameters of interest, so mu1 and mu2, and etc. This makes it harder to reject the null hypothesis due to a greater amount of error in our measurement, so a larger mean squared within. Now, what if we looked at an effect size, which does not take sample size into account for this test instead? Well, we can no longer rely on Cohen's d in this context because this statistic is only able to quantify differences between two means. But there is a useful and easily interpretable effect size in the context of ANOVA known as R squared, or alternatively, eta squared. Now, this tells us the proportion of total variance in scores around the grand mean that is accounted for by variation between groups. In other words, how much of the variance in our dependent variable is due to our independent variable. So the calculation of this effect size relies upon information we already have. And remember that S squared between and S squared within are the same as mean squared between and mean squared within. So S squared between times degrees of freedom between divided by S squared between times degrees of freedom between plus S squared within times degrees of freedom within. Now let's go calculate this for our adaptive memory example in the spreadsheet. Okay, so there'll be a lot of parentheses here since we have so many operations, but R squared equals open parentheses mean squared between, so F15, times degrees of freedom between, which is 2, divided by open parentheses again, mean squared between, F15, times degrees of freedom between, 2, plus, open parentheses, mean squared within, F16, times degrees of freedom within, which we remember is 12, so the number of total participants minus the number of groups, 15 minus 3. So that is times 12. Close parentheses again. So the R squared we get is 0.24. And that checks out here. R squared equals 0.237 or 0.24. Now, the interpretation of this is that 23% or 23.7% of the variance in memory for words is due to how these words were initially encoded. So being in that survive versus self versus pleasant condition accounts for 24% of the variance in how many words are remembered. And that's not super small. So recommended cutoffs for interpreting the magnitude of R squared are 0.01 is a small effect, 0.06 is a medium effect, and 0.14 is a large effect. And we had a very large effect here. 24% of the variance was explained as a result of our independent variable. Thus, despite a non-significant p-value, our effect is quite large for the IV in this study. This demonstrates the difference between null hypothesis significance testing procedures and the use of effect size estimates. A large effect might not end up being significant with a very small sample size. So now I'd like you to try this out on your own with the same set of data. And just follow along with me in the video. And that's all I have for this lecture. We'll be back with ANOVA 3 next time. Thank you.